In 1907, the longest cantilever bridge ever attempted was rising over the St. Lawrence River in Quebec. It was meant to be a symbol of progress, engineering confidence, and national ambition. But before it was completed, the structure began to show signs of strain. Warnings were noted. Calculations were questioned. Construction continued. On a late summer afternoon, without explosion or storm, the bridge folded into the river below. What followed would become one of the most significant engineering failures in North American history. At the beginning of the 20th century, Canada sought a permanent rail connection across the St. Lawrence River near Quebec City. The river was wide, deep, and subject to heavy ice movement during winter, making conventional bridge designs impractical. Engineers proposed an ambitious solution, a massive cantilever bridge that would surpass every similar structure built before it. The planned central span would be longer than any existing cantilever bridge in the world, positioning the project not only as a transportation link, but as a symbol of engineering leadership. The scale of the design required enormous steel members, complex calculations, and confidence in emerging structural theory. American engineer Theodore Cooper, one of the most respected bridge designers of his time, was appointed consulting engineer. The project moved forward with national attention and financial backing, driven by the belief that modern engineering could overcome natural obstacles through precision and experience. Construction began with confidence. Steel components were fabricated and shipped to the site, where they were assembled piece by piece, extending outward from massive anchor arms on either side of the river. As the structure grew, its size became increasingly apparent. Workers stood small against towering steel trusses, and each added section increased both the span and the weight pressing inward toward the center. The bridge was not merely large, it was unprecedented. The ambition behind it left little room for uncertainty. Success would demonstrate mastery over scale and mathematics. Failure, though rarely discussed, would expose the limits of calculation and oversight. As construction progressed, the weight of the growing cantilever arms began to exceed original estimates. The design calculations, completed before modern structural analysis methods were fully developed, underestimated the total load the steel members would be required to bear. Each new section added to the span increased compression forces in the lower chords of the bridge, particularly near the anchor arms. At first, these stresses remained theoretical, confined to drawings and numbers reviewed from a distance. But by the summer of 1907, engineers on site began to notice physical signs that something was not aligning with expectations. Certain steel members appeared to be bending slightly under compression. Measurements showed deviations from predicted behavior. Reports were sent to the consulting engineer, describing distortions in key components. The response was cautious but not urgent. Adjustments were discussed, and work continued while further analysis was considered. The prevailing belief remained that the structure, though immense, was fundamentally sound. Confidence in the original design discouraged immediate suspension of construction. The bridge had already consumed significant resources and attention, and halting progress carried both financial and reputational consequences. As steel continued to extend outward over the river, the margin for correction narrowed. The structure was no longer just a plan on paper. It was a physical mass of steel-bearing forces that calculations had underestimated. Subtle warnings were present, but they competed with optimism, authority, and the assumption that experienced engineers could resolve discrepancies before they became critical. By late August 1907, concerns about the bridge's structural behavior had become more difficult to dismiss. Engineers on site observed that several lower compression members were no longer merely deviating slightly from alignment, but showing visible distortion. Measurements indicated that the stresses within key components were significantly higher than the original design had anticipated. Detailed reports were again sent to Theodore Cooper, who was overseeing the project remotely due to illness. From a distance, he reviewed the figures and acknowledged that the weight of the structure had been underestimated. The bridge, as designed, was heavier than calculations had allowed. Yet the full implications of that realization were not immediately acted upon. Communication delays, reliance on revised estimates, and uncertainty about how severe the problem truly was slowed decisive action. At the construction site, workers continued assembling steel sections, extending the cantilever farther over the river. Each additional piece increased the load carried by already strained members. Some engineers recommended halting construction until a full reassessment could be completed, but work did not immediately stop. The structure had grown so large that reversing course was complex and costly. Authority was centralized, and decisions depended heavily on the judgment of a few individuals. As the final segments were prepared for placement, the bridge stood incomplete but immense, suspended over the St. Lawrence under forces that were no longer fully understood. The warning signs were documented, acknowledged, and debated. What remained uncertain was whether there was still time to correct them. On the afternoon of August 29, 1907, work continued on the southern cantilever arm of the bridge. Steel members were being positioned and secured as they had been on previous days. Shortly before the collapse, workers noticed unusual sounds coming from within the structure, sharp metallic noises that suggested shifting under stress. Some attempted to move away from the area, sensing instability. At approximately 5:30 p.m., a critical compression member in the lower cord failed. The failure was not explosive, but sudden. Once that element gave way, the forces it had carried were transferred to adjacent members, which were already operating beyond their intended capacity. Within seconds, the massive southern arm of the bridge began to buckle. The steel framework folded inward and downward, pulling connected sections with it. Nearly 19,000 tons of steel plunged into the St. Lawrence River below. The collapse lasted less than a minute. Workers on the structure had little time to react. 75 men lost their lives in the fall or were trapped beneath twisted steel in the water. The northern portion of the bridge remained standing, but the central span and southern arm were destroyed. What had been an unprecedented engineering project was reduced to a mass of submerged steel. The scale of the failure was immediate and undeniable. There had been no storm, no collision, no external trigger. The bridge collapsed under its own weight, exposing a miscalculation that had been embedded in its design from the beginning. In the hours and days that followed, attention shifted from the river to the reasons behind the collapse. Recovery efforts were limited by the depth and current of the St. Lawrence, and much of the fallen structure remained submerged. The scale of the disaster quickly drew national and international attention. Newspapers reported the failure as one of the most significant engineering catastrophes of its time. An official inquiry was established to determine how a project led by experienced engineers and backed by established firms could have failed so completely. Investigators reviewed design calculations, correspondence, and construction records. It became clear that the original estimates of the bridge's dead load had been substantially incorrect. The weight of the steel structure had been underestimated, and the design had not included sufficient margin to accommodate that error. As construction progressed and additional weight was added, critical compression members were pushed beyond safe limits. The inquiry also examined communication between the consulting engineer and the construction team. Reports of distortion had been acknowledged, but the seriousness of the situation had not been fully acted upon in time. Responsibility was distributed across multiple levels of oversight, revealing weaknesses not only in calculation but in decision-making processes. The collapse was not attributed to a single defective piece of steel, but to a chain of misjudgments rooted in confidence and incomplete analysis. The bridge had not failed because the concept of a cantilever was unsound, but because its scale had surpassed the reliability of the calculations supporting it. The disaster marked a turning point in how large engineering projects would be evaluated, but the inquiry itself was only the beginning of that shift. Following the findings of the inquiry, the project was not abandoned. Instead, plans were made to rebuild the bridge using revised calculations and stricter oversight. The collapse had exposed weaknesses in both design assumptions and supervisory structure, and these would not be repeated without scrutiny. A new team of engineers was appointed, and responsibility for design and construction was more clearly defined. Greater emphasis was placed on independent review of calculations, load assumptions, and material specifications. The revised design incorporated stronger compression members and adjusted proportions to better account for dead load and structural behavior under stress. Construction resumed several years later, proceeding with greater caution. Each stage was monitored more closely, and warning signs were treated with greater urgency. Yet the process remained complex. In 1916, during the reconstruction of the central suspended span, another accident occurred when a lifting operation failed, causing the span to fall into the river. Though separate from the original design miscalculation, the incident reinforced the risks inherent in large-scale engineering projects. Despite this setback, the bridge was ultimately completed in 1917. The finished structure stood as one of the longest cantilever bridges in the world, a physical reminder of both ambition and correction. The collapse of 1907 had reshaped not only this project, but the broader standards by which engineering responsibility and verification would be measured. The lessons were costly, but they became embedded in future practice. The Quebec Bridge Collapse remains one of the most studied engineering failures in North American history. It is remembered not simply for the loss of life, but for what it revealed about the limits of calculation, authority, and assumption. The design had been developed by experienced professionals using the best knowledge available at the time. Yet confidence in theory was allowed to outweigh emerging physical evidence. The warning signs were documented, but they were interpreted through a framework that assumed the structure was fundamentally sound. The collapse demonstrated that scale amplifies error. A small miscalculation, when multiplied across thousands of tons of steel, becomes irreversible. In the years that followed, engineering standards evolved to require more rigorous review, clearer accountability, and greater margins of safety in large projects. Independent verification of calculations became more common, and the profession placed stronger emphasis on ethical responsibility when concerns arise. The completed Quebec Bridge still spans the St. Lawrence River today, not only as infrastructure, but as a reminder of that shift. Its history underscores a principle that extends beyond one structure or era. Progress depends not only on ambition, but on the willingness to question it.